So good morning, everyone. What I'm going to do is talk about coupled modeling studies using CESM, which several speakers have talked about already, and combining that with atmospheric chemistry. And we'll talk a little bit more about why we're doing that as we go through here. And we're going to look at the question of how climate change is affecting air quality and what that means in terms of effects on human health as we look forward over this century, or particularly to mid-century. This is based on the PhD work of my student, Swarnali Saino, who is now Dr. Saino, since she's completed her degree in the last month. And and she's also going to have a poster here later this week. I don't know which day is. Today. So this afternoon she'll have a poster, and which will go in more detail about the studies I'm going to show. So let's get us started. Every year there are about 7 million deaths worldwide, according to the World Health Organization, related to air pollution. 4.2 million of those are related to outdoor air pollution, and the other 2.8 are largely related to indoor pollution, such as the use of cooking stoves that can cause health issues, and particularly in Africa and some other developing countries. The largest amounts of those deaths occur in India and Southeast Asia in general, but India and China. In the U.S. and the Americas in general, it's about 300,000, so we're much smaller in total number, but still we have a lot of major health issues, and we'll look at that in more detail. So this presents major challenges to those trying to do air quality management in cities, states, various localities in our country and in every other country. And the issues involve understanding the emissions, both human and natural, how after those emissions occur, how the gases and particles evolve due to chemical transformations and transport processes and the effects of various issues associated with weather and climate, resulting in the final concentrations and the resulting exposure and what that means to human health. If we just look at the climate effect, the biggest impact occurs from warmer temperatures. As we talk about things like ozone, ozone formation happens due to the emissions of nitrogen oxides in the presence of hydrocarbons or carbon monoxide, and then temperature plays a key role in the formation of the resulting ozone. So temperature plays a big role, but it's not the only thing. Shifts in weather regimes, how the jet stream changes, such as we were talking about earlier today, changes in things like the Bermuda High and how that can influence air pollution on the eastern part of the United States. Changes in storm activities and other impacts. Long-range transport of pollutants is also an important factor, and how that changes with the changing climate. For example, bringing pollutants from China to the United States is a key source of pollution on the west coast of the United States. And then there's other factors such as the effects of emissions from wildfires or dust storms and the particles that those put into the atmosphere. We're primarily going to look at the first three of these as we go through this, and we're not going to try to distinguish them. That's been done in some of our earlier studies, but instead we're going to focus on health. And the way we're going to look at health is through exceedances. Those are the days when pollution is high enough that the World Health Organization, or set by U.S. standards, for example, by the Environmental Protection Agency, say that those are particularly of concerns, days of concern to human health. In the case of the U.S. standard, For ozone, the 8-hour standard is, and ozone is primarily produced during the day and then decreases at night. So the 8-hour average is of a concern, and the US standard is currently 70 parts per billion. And it has come down over the years. The WHO standard, which is based on a number of published epidemiological studies, suggests that we really should be more like 50 parts per billion. So we're going to look at both in many parts in several different parts of the world. And in this study, while the analyses we do are global, we're primarily going to focus on the United States, China, and India. For particulate matter, we're particularly concerned about the particulate matter less than 2.5 micron. Those are the particles that can get into your lungs and cause major health issues. For the US standard, that is currently 35 micrograms per cubic meter. WHO suggests it really should be more like 25 micrograms per cubic meter, again, based on published medical studies. So like the other studies, we really need blue waters to do this kind of work. Not only are we using a complex climate model like CESM, but on top of that, we have pretty much complete atmospheric chemistry. And that more than doubles the cost of the runs and makes this extremely expensive. Because of that, we had to keep the resolution on the order of a degree. And that does affect what we're doing here. But these studies are actually going to feed into very detailed, much higher resolution studies of the United States. And primary funding for this work is through the EPA. And we're going to look at the impacts on climate and atmospheric chemistry on air quality in the 2050 time period. Particularly, we're going to look now historical and then 2050, and we're going to look at multiple scenarios. I'll say a little more about those scenarios as we get into them. Additional sensitivity studies for a clean energy world, clean energy future, is also looked at for 2050. Where we basically assume that there are no fossil fuel emissions by 2050, so much lower emissions than the other scenarios we're going to look at. So if we first look at the United States and look at both the US standard and the WHO standard for ozone, we find the various parts of the US and a number of major cities definitely have an air quality concern, with a number of days above, in many cases, much of the summer being above the US standard. And if we applied the WHO standard, almost the whole entire nation would be considered to have major health concerns in terms of the number of exceedances. If we look in the future, we looked at two cases, RCP 4.5 and RCP 8.5. 8.5 basically assumes that we will continue to heavily use fossil fuels through mid-century and beyond, and corresponding to that as an overall an increase in emissions that cause more air pollution. So it's the use of fossil fuels is a primary source not only of greenhouse gases that affect climate, but also are the primary concern related to air quality concerns. RCP 4.5 assumes by mid-century that we have rapidly moved away from the use of fossil fuels, but until then, emissions are still increasing to some degree. So if we look at those two cases for the US ozone, we see overall a significant reduction in the number of days with exceedances for ozone, both applying that to the US standard and the WHO standard. But still, in some areas, a remaining significant number of days with the high scenario. And in fact, if we looked at some cities, we see that WHO standard almost every day of the year exceeds the standard because the background levels of ozone have gotten so high. A couple of cities in the US we didn't really model very well, and that's because the ocean influence can't be modeled at 1 degree by 1 degree grid, or 0.9 by 1.25 degree grid that we used. And so Los Angeles and Houston are really not representative of the amount of air quality issues in those cities. But in general, we see with the RCP 4.5 that there is a reduction in US cities in amount of ozone exceedances. For some cities, a rather drastic reduction. While what RCP 8.5, there's still some increase in some of these cities. Now, if we look at Southeast Asia, looking again at the historical versus the two scenarios, using the US standard, and every country, by the way, has its own standard, but we decided to use these two as probably being better representative of where people should be at in the world. Although some countries say they apply the WHO standard, they actually don't because they're not enforcing it. But the US standard is enforced in the United States, and so we thought it would be useful to look at that as well. So looking at India and China, generally in India, as you see, the amount of exceedances tends to increase, depending on what part of India. And in China, as we saw with the United States, the RCP 4.5 scenario generally is a decrease, and some of an increase in some areas with the higher scenario. Again, if we look at some of the cities, in this case for China, we see just what I mentioned, that for RCP 4.5, there's generally a decrease and an increase, about the same or an increase for the higher scenario. If we turn to India, all seasons, or both scenarios show an increase in the amount of ozone. The other thing we find is that whereas we used to think of summer as primarily being the time when we have concerns about particularly ozone, the exceedances are expanding in the future such that other seasons are now seeing many, many more exceedances than they did in the past. So even though there might be an overall reduction in emissions, because of the warmer temperatures, you're still seeing an increase in exceedances at times. And that's both in the United States and the other parts of the world we looked at. Turning to particulate matter, the United States, following the US standard, generally sees a significant decrease, and that's also found with the application of the WHO standard. We'll see that again if we look at cities where generally there is a decrease in the overall emission, or the overall exceedance days, but not always. You know, some scenarios, some cities we do see a slight increase, but it's very slight, such as Denver, for example, where it's really increasing by a few days per year. Turning to South Asia again, we see a significant increase in the projection for PM 2.5, both with the US standard and with the WHO standard. In India, the number of days increases in both scenarios. In China, the number of days increases, particularly in the high scenario, and a slight reduction in the low scenario. Looking at some of the megacities, China generally follows that same thing, where Beijing tends to see a slight decrease in the number of exceedances under the low scenario and a slight increase under the high scenario. Looking at India, both scenarios tend to show a significant increase, depending on which city is looked at. Now we're going to turn to the clean energy scenarios. currently about 80 to 85% of the energy and transportation production around the world is related to fossil fuel use. So in this scenario, we assume that that use drops to zero. A very ambitious scenario, but we did assume that emissions from the use of biofuels would not decrease relative to the scenarios. And in some cases, those are considered to be replacements for the use of fossil fuels in the RCP scenarios. And we still include burning of crops and things like that, so other bio-related emissions, or agricultural fields and that kind of thing. And then oceanic and other natural sources are assumed to remain constant as they were in the other studies. So if we look now in terms of, this is in concentrations of ozone, not in terms of exceedances, that the overall amount of ozone produced around the world drops by a large amount relative to the RCP 8.5 scenario, such that, as you will see, corresponding to that is a very significant decrease in the number of exceedance days as well. Likewise, if we just look at the summer concentrations, when we generally, these days, expect the peak concentrations to occur, and we will likewise in the future, just the amount of seasonal production of ozone will tend to increase over time, over the coming decades, that we also expect a significant decrease in the amount of ozone in over most of the land areas of the world. Turning to PM 2.5, again looking at concentration, many places again see a projection of a very significant decrease with the clean energy scenario. In this case, it's plotted a little differently. It's total PM 2.5 on the top, so it includes the natural sources of PM from dust and sea salt, for example, in the top, whereas the bottom only shows the anthropogenic production. So that anthropogenic production, for example, in Africa, shows a remaining large amount, but that's primarily from biomass burning. Whereas the clean energy and scenarios in general otherwise show a very significant reduction in emissions, or in the amount of PM 2.5. Now, if we turn to looking at exceedances, the exceedance days, both for ozone and for PM, decrease globally. Surface ozone concentrations are reduced by 40 to 50% annually, and in the summer by 30 to 50%, reducing the exceedance days over the hotspot regions by over 70%. Total PM 2.5 concentrations are reduced by 20%, especially over South Asia. Removing the fossil fuel completely improves air quality significantly throughout the planet, greatly reducing the amount of likely health issues. The exceedance days over North Africa that are still seen are dominated by dust and as I mentioned earlier, somewhat by biomass burning. For conclusions, this study is focused on health impacts of a changing climate on air quality. A number of previous studies that we've done have looked more at just the changes in ozone and PM. Now we're looking at this somewhat differently and looking at the different factors that drive those changes. How changing climate impacts on air quality in the United States, China, and India are all looked at in terms of exceedance events. And the impact of an idealized clean energy world on air quality is looked at from mid-century. For the high scenario, air quality degrades in India and in China, and exceedance days increases from the present regionally. Air quality generally improves over the United States with those scenarios, even for the high scenario. The clean energy future scenario results in a world with significantly improved air quality, resulting in a significant reduction in air quality related health issues. And I thank you.